In this video, we're going to take a look at Java arrays. Let's say we have two classes, A and B, and that B is a subclass of A. And let's think about what happens when we execute the following piece of code. So the first thing we're going to do is we're going to allocate an array of B's. So this is an array that's supposed to hold B's. Okay, and we're going to have an array variable, little b here, that points to it. And then we're going to have another variable, array variable A, that also points to the same array as B. But notice the type of A. So A is an array of A's, little a here is an array of A's, and B is typed as an array of B's. And now what we're going to do is we're going to assign into A sub 0, okay, into the first position of A new A object. And that should be fine, right? Because A is an array of A's. And that seems like that should work out all right. All right, so here there will be an A sitting in the first position. And then we're going to access B sub 0, which, because A and B point to the same array, is the same element as A sub 0. And we're going to call some method that is not declared in A. Now remember, B is a subtype of A. All right, so B has all the methods of A, okay, but B might have more methods. And since this is an array of B's, we should be able to call all the B methods on it. And yet here, when we call some method that's declared in B but not in A, we're going to get a runtime error because the object that's stored in the array is actually an A object at the first position. To understand what's going on in this example, we have to take a look at the subtyping rules in Java. So B is a subtype of A if B inherits from A. That's one case. So if B immediately inherits from A, then B is a subtype of A. And that's just like in COOL and most other object-oriented languages. And we're very familiar with that from our lectures on type checking. Furthermore, subtyping is transitive. So if C is a subtype of B and B is a subtype of A, then C is also a subtype of A. Okay, and that's also completely standard. But then there's this other rule that's not quite standard, or it is definitely non-standard. And that's that an array of B's is a subtype of an array of A's if the element types are in a subtype relationship. So if B is a subtype of A, then array of B is a subtype of array of A. And COOL doesn't have anything like that. COOL doesn't have arrays, so it wouldn't even have the opportunity to have something like that. But this is also not the way it's done in other languages that have objects and subtyping. So let's take a look at our little example again, and let me explain it in a slightly different way. So the issue here is that we have an area of memory, and it actually doesn't matter here. It's not essential that this be an array. What's important is that it's an updatable part of memory, so that we have pointers to it. We have two pointers to it, A and B, and they can both read and write this part of memory. So this could be just a single cell, doesn't have to be an array of multiple cells. But what's important is that there is some memory location that both of these point to that they can both read and write. Okay, and the trouble comes, and by the way, there's a name for that. That's called aliasing. Okay, so when you have two names, two program names for the same part of memory, that is called aliasing. And here, we have the two arrays A and B that point to the same area of memory. Okay? Now, aliasing is very common in real programs, and it's not bad by itself. But the problem in this example is that A and B have different types. Okay, and in general, if you have aliasing, updatable references, okay, meaning you have two names for the same location, that location is both readable and writable, so it can be updated through the two names, and those two names have different types, then that is going to be unsound. Okay, you're not going to have a sound type system. And to see the problem, let's say here in this case, what was it? We had that B, type B, was a subtype of A. Okay, and what did that mean? Well, that meant that we could do a write through this pointer, okay, and write an A object into this location. And then we could read that out through this pointer over here as a B object, but now it doesn't have all the methods and fields of A. And treating it as a B object, we can potentially do some operation on it that's undefined. And you can see that it doesn't help if we swap the roles of A and B. All right, so if in particular, if we reverse the subtyping relationship so that A was a subtype of B, we get exactly the same problem because aliasing is symmetric. Then we would just do the write through the B pointer and the read out of the A pointer, swapping the roles of the reads and writes here, and we'd have exactly the same problem. So in general, multiple aliases to updatable locations with different types is unsound. Right? And this problem actually has come up in many different programming languages. Java is not the only programming language to have had this issue. It's a fairly subtle aspect of type systems, and many languages have done things similar to Java where they've created a problem really for the static type system by wanting to have subtyping work through arrays. Now, the standard solution, or the solution that's used in, I should say, in many languages and is probably most widely accepted in the programming languages research community, is that you need a different subtyping rule for arrays. So we would say, the rule that is commonly used, the standard solution to this problem at the type level is to do the following thing. So you only allow subtyping on arrays. So an array of B's is a subtype of an array of A's only if B and A are the same type, if B is equal to A. And if you think about that for a second, if we have an array and now we have our two pointers to it, A and B, and we know the type of A is a subtype of the type of B, well, that only happens if the element types are equal, and so we can't create two references to an updatable location with different types, okay? And that will guarantee soundness of the type system. So Java fixes the problem differently. So instead of statically checking that array accesses will all be type correct, Java does this at runtime. And so whenever an assignment is done into an array at runtime, Java checks whether the type of the object being assigned is compatible with the type of the array. So when you say new B sub 10 in Java, Java will remember inside the array that this was supposed to be an array of B's. And then whenever you assign into the array, it will check that the thing you're assigning is either a B or a subtype of B. Now this obviously adds overhead on array computation. So every assignment to an array is going to have a type check on it at runtime. And fortunately though, the most common kinds of arrays are arrays of primitive types, in particular arrays of ints and arrays of floating point numbers. And these are not affected because the primitive types are not classes. There's no subtyping on them. And so you can never create an array, say, of floating point numbers with any kind of subtyping relationship that would result in this problem. So we're saved or in better shape for the primitive types, and they don't need these extra checks. But if you have arrays of objects, then when you do assignments into those arrays in Java, there's additional runtime overhead.